Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan Hakim bin Ahmad Izamuddin. Today I would like to present about detection of metal contaminants in local wild and cage barramundi or latest Carosarifer via inductively coupled plasma optical emission spectroscopy (ICP-Oes). The content will be divided into 9 parts, which the first one start with introduction, problem statement, research question, objective, literature review, methodology, result and discussion, conclusion and recommendation also with reference. Let's go with the introduction first. Lettuce calcifer, also called as Barramundi or Asian sea bass, is widely consumed in Malaysia, both from wild catches and commercial catches farming. Metal accumulation in Barramundi affect consumer health and food safety. This study examined contamination rates from cadmium, lead, zinc, and ferrum, evaluating metal content differences for consumer safety based on Malaysian Food Act and regulation. Now let's continue with problem statement. Marine pollution influence metal accumulation in fish, including barramundi, a key food sources in Malaysia. Consuming contaminated fish poses health risk, making regular monitoring essential to ensure safety per Malaysian Food Act and Regulation 1985 and WHO FAO 2004 guideline. However, limited research compare metal level in wild and farm barramundi, highlighting the need for comprehensive study using ICP-Oes. Understanding contamination sources can improve food safety policy, sustain fish population, and help consumer make informed choices. There are two research questions in this study. First, what is the level of metal contaminant in cultivated lettuce calcarifer compared to those in wild lettuce calcarifer when analyzed using inductively coupled plasma optical emission spectroscopy or ICP-Oes? Second, are the concentration of detected metal contamination in cultivated lettuce calcarifer and wild lettuce calcarifer within the safety limits set by the regulation and guidelines? There are two objectives from this study. Firstly, to compare the level of metal contamination in the wild and cage lettuce calcarifer, and secondly, to evaluate the safety of wild of lettuce calcarifer and cultivate lettuce calcarifer based on the Malaysian Food and Regulation. From the significance of study, this research is crucial due to the high demand of the lettuce calcarifer in Malaysia and its nutritional benefit. Industrial pollution worsened metal contamination in fish, posing a health risk by comparing wild and farm barramundi. The study provides insight for food safety regulation under the Malaysian Food Act 1985 and WHO FAO 2004. Aligning with the 12th Malaysian Plan, it supports sustainable resource management, marine biodiversity protection, and the development of the integrated food safety system using ICP OES analysis. Let's go to the part of the literature review with the background of lettuce calcarifer. First, the taxonomy. Lettuce calcarifer belongs to the Lattidae family and is an economically valuable species in Malaysia. With the scientific name is lettuce calcarifer and common name or also known as barramundi, or in Malay we call it siakap. Morphology. Lettuce calcarifer has moderate, deep, elongated and compressed body with concave dorsal profile of the head. It has deeply incised dorsal fin and long third anal fine spin around the caudal. Ecological adaptation. Roline and Cotodramus species, which also a carnivore, feeding on crustaceans and shrimp and small fish. Let's go with the basic principles of ICP-OES. Firstly, a liquid sample is injected into a nebulizer where it's converted into an aerosol. Argon gas is ionized in torch coil, creating a high temperature plasma that excites the atom in the sample. Excite atom return to their ground state, emitting light at characteristic wavelength specific to each element. The emitted light is captured by optical system and its intensity is measured to determine the concentration of element in the sample. ICP-OES has been widely used to analyze trace metal in food such as infant formula and honey. Now let's proceed with the methodology. The methodology of this experiment divided into 4 parts: sample collection, sample cleaning, sample preparation, and sample analysis. For the sample collection, 5 cages and 7 wild lettuce calcarifer sample were collected from Pasar Besar Sena Kangapelis within between 700 gram and 1000 gram. Freshness was assessed based on the eye clarity and the gill color. Before starting with the acid digestion, the sample were cleaned with tap water to remove dust and residue, followed by rinsing with distilled water to eliminate potential metal trace. All apparatus was decontaminated by soaking in with 10% of nitric acid before analysis. Before undergo with the ICP-Oes analysis, the sample need to be undergo acid digestion. Acid digestion was conducted in the fume hood to prevent exposure to acid fume and contamination. The process used 65% of nitric acid, 37% of hydrochloric acid, and 30% of hydrogen peroxide as the key reagent. Uh, Nitric acid is a oxidizing agent, breaking down organic matter such as protein and lipid, while hydrogen peroxide further decompose remaining organic material to ensure complete digestion. And hydrochloric acid was added in the final stages to convert matter into their chloride salt for better solubility and analysis. Next, the sample that has been complete with acid digestion then filtered with a filter paper and diluted to 25 ml. Before ICP-OES analysis, the final solution will filtered through the 0.45 micron syringe filter to remove impurities. Let's look at the result of the white sample. There are 7 samples here, and from the mean of the cadmium, lead, zinc, and ferrum, all the elements were below from the FAR or Food Malaysian Regulation 1985 and WHO, which is permissible and safe to consume. If you look at the data before, cadmium was below detection limit or BDL, likely due to extreme low concentration in the fish sample. The machine software may have subtract baseline noise, leading to small negative value when the CD signal was too weak. The low lead concentration suggests low anthropogenic contamination, such as factory and mining contamination. Some metal like zinc and ferrum may be stored in other parts of the fish, such as liver and gill, or even in intracellular compartment, reducing the presence of metal in the muscle tissue. Now, let's look at the cage sample. There are 5 samples here, and if you look at the cadmium, lead, zinc, and ferrum, all the main were shown below from the FAR 1985 and WHO, which is the regulation standard we use here to compare the safety of consuming the sample. If we look at the case sample from the sample 1 and sample 2, all the data we given obtained were negative. There are several reasons for this. Firstly, fish do not accumulate matter uniformly even in the same environment. The overall low matter level suggests minimal contamination in the cage system. Matter concentration in the water may not be perfectly uniform, leading to variation in accumulation. Incomplete digestion process for some sample, metal extraction could have been lower, leading to non-detectable result. Now, if you look at the sample 3, 4, and 5, there are also several reasons for the cadmium is negative. Firstly, fish accumulate heavy metal at different rate depending on their metabolism, feeding behavior, and exposure of duration. The overall low metal level suggests minimal contamination in the cage system. Fish in the different section of the cage may be exposed to slightly different metal concentration due to the localized variation in the water flow, feed dispersion, and sediment interaction. Variation in muscle structure, fat content, or enzymatic activity could lead to different metal absorption level. For the conclusion part, this study analysed and compared heavy metal contamination, which is cadmium, lead, zinc, and ferrum, in wild and catch lettuce Calcarifer, revealing differences influenced by environmental and farming conditions. Both wild and catch lettuce Calcarifer were assessed for food safety based on the Malaysian Food Act and Regulation 1985, ensuring compliance with permissible metal limits. All analysed metal concentration were within the safety limit, confirming that both wild and farm lettuce Calcarifer are safe for consumption. This finding emphasized the importance of continuous monitoring to maintain food safety standards. There are several recommendations in this research. Firstly, collecting a large number of samples will provide a more comprehensive representation of heavy metal concentration variation in seafood. And secondly, analyzing additional tissues such as liver, gills, and bones can enhance understanding of metal bioaccumulation pattern beyond muscle tissue. Collecting fish sample directly from farming system will ensure more accurate comparison between wild and catch lettuce Calcarifer, collaborating with suppliers, local fish farm and fishermen to document fish origin and catch method will improve data reliability and traceability. Incorporating water quality analysis and sediment testing can provide insight into the sources and extent of metal contamination in fish habitat. That's all from me. Thank you.